Hi dear students, welcome back to my session. In our previous session, we discussed Thevenins theorem and the procedure. In this class, we are going to discuss few problems on the Thevenins theorem. Right? Let me move to the next slide. So already you know the basic concept of Thevenins theorem, and you know the electrical basic equivalent circuit of Thevenins theorem. We denoted as a in tech Thevenins equivalent circuit. So just I want to brushing up your knowledge. Already you know the concept of Thevenins theorem. Just I want to quick forwarding of the slides. Consider the following. Just like this is network 1 and network 2 coupled networks. For the purpose of discussion at this point, we consider that both networks are composed of resistors and independent voltage and current sources. Means here Thevenins theorem can be applicable to this circuit. In our previous session, we discussed based on the statement, but in this session, we are going to be discussed based on the examples. Means based on the actual physical content on the circuits. Means physical content actually we may have the independent voltage sources and current sources with the composed of resistors. So in this network one. So in this network one, let me add my marker. So in this network 2 and network 1, sorry, this network 1 and network 2, we have the composed of resistors, means R1, R2, R3, like the composed means a different value of resistors in this network 1 and network 2. So that is the meaning of coupled network. So suppose network 2 is detached from the network 1 and we focus temporarily only on network 1. So here the network 2 is nothing but a load. Then network 1 is an open circuit. Network 1 can be complicated in structure as one can imagine. Maybe 45 meshes, 387 resistors, 91 voltage sources, 13 current sources. I took as random numbers. So 45 meshes. So don't mug up this numbering of the meshes. Just I took the random examples. If in the network 1 maybe contain 45 meshes, 387 resistors or 400 resistors, 92 voltage sources, 39 current sources may be there in network 1. So how we are going to be converted those complicated structure into the our equivalent way of structure, that is called Thevenin's equivalent circuit. So that is the network 1. So network 2 is nothing but a as I already said, that is a load. Now place a voltmeter across the terminal A and B. This is A and B, and read the voltage. Means if you have the voltmeter, means n number of resistors, n number of meshes, and the very n number of voltage sources and n number of current sources are there. If you assume that I number of current sources, m number of meshes, r number of resistors, vn number of voltage sources may be there in network 1. But I'm going to be convert complete those complicated structure of these in the network 1 into the one equivalent circuit. So how I'm going to be converting? Let me measure by using the DMM. As you know, DMM is a digital multimeter. By using this meter, you can measure resistance, and you can measure the voltage, and you can measure current, right? So if you measure over here, in this here we have two probes. One is a red probe, second one is black probe. So by using these probes, you can connect over here. By correction, directly you can measure voltage over here. You may have some voltage across this network 1, that is called Thevenin's voltage. Means that also you call Thevenin's voltage, VTH, also called. So you can measure voltage by using DMM directly. So this is one practical way of measuring the voltage. But in theoretical way, you should measure the voltage across the AV. There is some procedure is there. Already you know that procedure. In previous session we discussed. But even though we will, I'm going to brushing up your knowledge here. So here, so now place a voltmeter, or you can use DMM voltmeter across the terminal A and B. Why I said the DMM is internal, the voltage sources also is a present in the network one. That is the reason you can use voltmeter. Voltmeter is doesn't require any supply, but DMM you should have some internal battery. You can measure. For the measuring of DMM you require in the internal battery, but for the measuring of voltmeter you doesn't require any battery. Just you can plug it at A and B, then you can measure the voltmeter, because the battery itself is there in the network one, so you can measure directly. So we call this is a open circuit voltage. This is called VOC, V Thevenins, also called VOC, V open circuit voltage. Already you know what is the meaning of open circuit and what is the meaning of short circuit. This is VOC, VTH or VOC, both are same. So no matter how complicated network one is, we read one voltage. So this word is very important. How much complicated it is doesn't matter. You can read only one voltage across this A and B terminals. We read only one voltage. It is either positive A with respect to B or negative A with respect to B. So we call this voltage is V output source voltage. We call this is a Thevenin's voltage. VOS we call Thevenin voltage or VTH. So this is what I want to explain about this slide. So next, let me move to the next slide. So in this slide, I want to give important points to you. We now deactivate all sources of network one. To deactivate voltage sources, we remove the source and replace it with short circuit. Deactivate the current source, we remove the source. So here I already said for the removing of voltage source means that voltage source, if the voltage source have the two types, one is ideal voltage source, one is a non-ideal voltage source, right? It means practical voltage source, one is ideal voltage source. So for the practical voltage source, if the replacing with the voltage source may have the some internal resistance, that is the can be replaced with this value. But if I use the ideal voltage source, that is going to be replaced with the short circuit. What I said in the wording. So what I want to say is voltage sources can be removed with the replacing with the internal resistance, and the current source can be removed with the internal resistance, but it can be removed by showing the output circuit. Right. So this is the one of the circuit how I'm going to be implementing those points. This is figure 1 and figure 2. This is figure 1, figure 2, and this is figure 3. So in this figure 3, the typical circuit with the independent sources. These are the independent sources. Don't bother about the dependent sources. As per the diploma syllabus, the dependent sources is not comes under your syllabus. So if you move to the graduation level, they may have the discuss about the dependent sources. Right, here in figure 3, the typical circuit with independent sources, you have a lot of sources, three voltage sources and 2 current sources. How do we deactivate those sources of the circuit? So let's observe V1, V2, V3. How this is going to be replaced with this circuit? Let me observe figure 4. In this figure 4, see here, this is going to be replaced with this. See, observe this V1, V2, V3. These 3 are going to be replaced with this short circuiting. See, 1. This is 2. Sorry, this is 3. Right? This is 3 short circuit. Next, what about this? Let me change my color. One and 2 is going to replace in open circuit. I already said 2 rules. 2 rules are very important. Sorry, 3 rules are very important. First rule is remove the load. Second rule is replace with the voltage source with short circuit. Third rule, replace with current source with open circuit, or remove the current source. That is the Thevenin's basic rule. So here I remove. Now after removing, see, observe R1 and R2 are both are parallel. See, R1 R2 are parallel. So let me change my color. R1 R2 are parallel. Let me change my color. See, R1 R2 both are parallel because those are connected to the common circuit, because since this is in open circuit. Since this is in open circuit, you can remove this circuit. If there is a value of resistance is there, this R1 R2 is not a parallel. So R1 R2 are parallel. Then after the parallel, R1, R2 will be series with the R3. Then R3 will be parallel with R1, 2, 3 will be parallel with R4. Then you will get R Thevenins resistance across A and B terminals. That is what I am going to be explaining in this point. Now place a ohm meter over here. You can use DMM. Already I said in previous session, you can use DMM. So you can use same DMM by measuring of the ohmic value, means by using ohm meter. You can use same DMM by keeping the resistive mode. Then you can measure the resistance across this directly. That is the practical way of finding the method. But in theoretical, you need to be measured. But theoretical, there is a procedure is there. We are moving to that procedure only. In practical, if you measure this resistance, it will come. If there is R1, R2, R4 is 20 ohms, R1, R2, R4 is 20 ohms, R3 is 20 ohms, then you can read 10 ohms across this value of this resistor, this A and B terminals. Right. Let me move to the next slide. This is the Thevenin's equivalent circuit. Already you know in figure 7. We call the ohm meter reading under these conditions R Thevenins or RTH, shortened RTH. Therefore, the important results that we can replace network 1 with the following network. So I am going to replace the entire network into the two elements. One is active element, one is passive element. So I said there are total 45 voltage sources and 387 resistances and 92 voltage sources, 132 current sources, like that. All those elements is going to be replaced with the one very mini compact circuit that is called Thevenin's equivalent circuit. In this Thevenin's equivalent circuit, we have only two elements. One is active element, one is passive element. That element is called voltage source, which is series with the resistance. This is called the equivalent circuit, also called ideal, non-ideal voltage source. So non-ideal voltage source also look like same way of representing. Already, if you have any doubts, please go through my previous sessions. You can observe the non-ideal and ideal voltage sources. So this is called same equivalent circuit of non-ideal voltage source. So in this, V Thevenins is series with the R Thevenins, right? Hope you're clear about this slide. So this is called tech. What is this called? Tech, Thevenins equivalent circuit. Right. So now I'm going to be attaching this network to. So whatever we got, this is completely neutralizing all the network elements, network 1 into this VTH and RTH. Now I'm going to be attaching this network 1 into the network 2. Whatever the elements contain the network 2, that doesn't matter. Here I'm taking the network 2 as a load. So here we can now make these calculations we desire within the network 2, and they will give the same result as we still hide the network 1 connected. So here the system figure 1 with the network 1 replaced with the Thevenin's equivalent circuit. Whatever I am going to be replaced with the Thevenin's well. So this is connected to network back to the terminals A and B. So this is network 2, already I said. So we can now make any calculations we desire within the network 2. They will give same results as if we still hide the network 1 connected. So whatever we are doing the same things, it is going to be will give the same results of network 1. As soon as whatever we are network 1 is connected, the same values will be comes to the across VTH and RTH. That's what I want to say by using this point. Means the changes is going to be affected on the VTH and RTH, right? So this is the network 1 and this is network 2. I'm going to be summarizing this network 1 and network 2 by using this way of representing. It follows we could also replace the network 2 with a Thevenin's voltage and the Thevenin resistance. The result would be as same as figure 7. If you have any voltage sources on the load itself, you can voltage sources and current sources, lot of resistance are there on network 2 itself. You can replace the entire network 2 by representing this Thevenin's 2 and RTH. So you can use, but irrespective of those all these elements, if you have only value of resistances, you can use that is a network 2 by deducting by reducing the resistances on the network 2 elements into the common resistance, that is R load. So this is about this slide. So I'm using one example for the clear understanding of this. Thevenin's theorem. Please observe this carefully. Here, find Vx by first finding Vth and Rth to left of A in B term. In the question itself, I given what to find. So this is voltage source. These are the resistances: 12 ohms, 6 ohms, and 4 ohms. So I am going to be measure Vth and Rth across this A and B terminals. So after measuring of Vth and Rth across this A and B terminals, I am going to be attach that Vth Rth to Vx, means 2 ohms resistor. Hope you clear. So first remove the right side part of A-B terminals. So I'm going to be removing, that is my rule number 1, all that I said. So I removed this load. Then I'm going to be measure the VTH across this A and B terminals. So here for measuring of VTH, so this is 4 ohms, not drawing any current. Since there is a no current drawing through 4 ohms, then this is completely not in active mode, means there is no voltage drop across this 4 ohms resistor. Then I am going to be removing this 4 ohms resistor by making this short circuiting. Why the current is not flowing this 4 ohms resistor? Because A and B are open circuit. Since current will not flow in the open circuit path, right? So that is why I removed this. So by after removing, this is showing like this. By removing, so I am going to be removing this 4 ohms. The entire voltage will be appear across 6 ohms. Same voltage will be appear across A and B terminals. So if I measure 6 ohms, the same voltage will be appear across VAB. That VAB is nothing but a V Thevenins, right? So for the measuring of 6 ohms, I use the VDR, voltage division rule. So total voltage multiply with the resistance, which I am going to be finding the voltage across the resistor. So same value of resistance by total resistance, 6 plus 12, then the 10 volts will be appear across this 6 ohms resistor. The same 10 volts will be appear across VAB. If you using DMM across this A and B terminals, 10 volts will be appear over here. So same thing. So this is 10 volts. This is VAB. 10 volts. The same 10 volts will be appear over here. So notice that there is no current flowing in the 4 ohms. What I given this point is clear here. Since that is a no voltage across the resistor, means no voltage. I need to be measured the no voltage drop across the resistor. Please make a note. Right. I move to the next slide. Here in this slide, I find VTH. Now I'm going to be find RTH. For the finding of RTH, we now deactivate the sources to the left of AB. So this A and B. So this is AB. I'm going to be deactivating sources, means the voltage sources are replaced with the short circuit. The current sources replaced with the open circuit. Here there is a voltage source is there. I'm going to be making this short circuiting. Right. So after the making this short circuit, this 12 and 6 is parallel. After the 12 and 6 is parallel, the result will be series with the 4 ohms resistor. Hence the value will be 8 ohms. If you have any doubts, please do it from your side. So this is circuit to find RTH. So this is RTH. You can measure in practical way. You can use DMM. On the DMM, you can measure ohmic value of this network. So this is way of finding RTH. In this slide, we find VTH. In this slide, we find RTH. So this is not VAB. You can name it as a 10 volts is a VTH. You can use small capital, that is your interest. So in this, I'm going to be adding, means I'm going to be attaching this VTH, and this is network 1. I'm going to be adding this network 1 to the network 2. Here this is the network 2. I can name it as this is network 2. and this is network 1, this is network 2, and this is the network 1. The entire circuit right side of, sorry, left side of AB is network 1 to 1, right side of AB is network 2. So I'm going to be add this network 1, which I reduced, which I neutralized to, summarized to VTH and RTH. So which are in attached to the network 2, that across A and B terminals. So here VTH and RTH is there. This is the load. So I can mention this is RL. This is load RL. So here I'm going to be measure by Vx by using this values. Vx is nothing but here by measuring of Vs across 2 ohms resistor. You can use VDR, voltage division rule. In the voltage division rule, total voltage multiply with the same value of resistance by total value of resistance. Here the same value of resistance is 2 ohms by total value of resistance 2 plus 8. Then the answer will be 2 volts across this Vx volts. In some problems, they may ask the question, what is the value of load current IL? For the measuring of IL, you can use directly IL is equals to V by R, right? Here the resistances are two values of resistances. Here one is RTH, one is RL. So you need to be add those values of resistance, since those resistors are connected in series. Then 8 ohms plus 2 ohms, the answer will be 10, and the this is value of resistance is 10, and the value of voltage is also 10. Then the 1 amps of current which is flowing through the load. So hope you got what I'm trying to say. This is very important way of understanding this Thevenins theorem. So in some problems they may have the ask the find the current flowing through the load. So in that type you can use this this formula for the finding of current, the simple Ohm's law, total voltage by total resistance throughout the line, right? So this is the finding by using the example number 1 by using Thevenins theorem. Let me move to the some other way of understanding. So in this, in some cases, it may become tedious to find RTH by reducing the resistive network with the sources deactivating. Consider the following. A Thevenin circuit with the open output shorted, we see RTH is equals to VTH by ISS. So here ISS is the maximum value of current which is flowing through this VTH. If in case I'm going to be considering in this type of case into the example number 2. So in this example number 2, I am going to be using this short circuiting path across this A and B. So this is one of the example. If the load is short circuited like this, so I am going to be make few more points before this load C and D. So here I am across the C and D. If the load is short itself, means there is a problem itself load. So since that is not a load, so I moved that load. AB is not a actual load. I moved to the imaginary load is nothing but a C and D. So if I move the point to C and D, then this is entire part will look like a load, right? So this is network 2. So this is network 2. So I'm going to be actually A and B is a load, but load is short circuited here. So for the finding of exact current, short circuit current, I'm moving to this load into the C and D point. So across the C and D point, even though if I open circuited this, I can't able to measure this total value of resistance. So hence, I'm going to be measure the voltage across this C and D, and I'm going to be measure the RTH across this C and D points. Then it should be look like this. So this is C and D. Across the C and D, I'm going to be measure. Let me remove this point, this entire point. So I'm going to be measure the VTH. For the finding of VTH, same value 30 volts multiply with the 6 by 12 plus 6. Then the VTH will be 10 volts. Then what about this resistance RTH? RTH is, this is going to be short circuited. Now 12 into 6 by 12 plus 6, 72 by 18. Then it will be RTH will be 4 ohms resistor. So this is VTH and RTH, 10 volts and 4 ohms resistor. Hence this is 2 are in series with the 4 ohms resistor. Right now it is very easy to find the ISS. What is the value of ISS? ISS is very simple, 10 by 4 plus 4. Then it will be 10, 9, 4 plus 4, right? So for the finding of this 10 by 4 plus 4, it will be some value 2 by 5 by 4. But here in the question I given clearly, find the RTH by using equation number 1. Means for the finding of RTH across this A and B, I used two imaginary points C and D. But here up to here I measure VTH and imaginary RTH, but this is not actual RTH. Whatever I used this is imaginary RTH. Imaginary RTH, but the measuring of RTH you should depend upon the total value of the resistance. Then for the measuring of RTH you should consider this complete resistance, that is 4 ohms. For that you should make a short circuiting of this, or you should depend upon the, for the measuring of RTH is equals to V by ISS. V by ISS. Already you know V, 10, ISS is nothing but 10 by 8, then the answer will be 8 ohms. This is a one way of procedure by using the same short circuiting path. But another way of procedure, how you can remove this A and B terminals directly. You can measure this after the connecting the load. After the connecting load, you can get directly 8 ohms resistor. That is one way of procedure. Already that is common procedure. Means whatever we follow in the example number 1, that type of procedures also you can use. You can use for the solving of this finding of RTH. But before without removing ISS also, you can find the RTH by changing my AB points to the imaginary points C and D. Over the C and D points, I am going to be find the VTH and the imaginary value of Thevenin's resistance. That imaginary value of Thevenin's resistance is going to be series with this one of the resistance which is in real value of resistance, that is 4 ohms. So then 4 plus 4, then 8 ohms value of resistance will be present across this RTH. So this is one of the different way of solving this Thevenin's theorem. So here I am going to be take example number 3. In this example, here I am using current source. So let me find Thevenins and the Thevenins voltage source and Thevenins resistances. Sorry, Thevenins resistance across A and B terminals. Here I clearly given A and B terminals, means A and B, across this A and B, this is the load. So my rule 1, remove this load, right? We first find the VTH with 17 ohm resistors removed. Next, we find RTH by looking into the terminals A and B with the source deactivated. These are the steps we are going to be performed on the next slide. So I removed the load. Then after the removing load, I am going to be find first VTH. For the finding of VTH, so this is the, please understand the steps clearly. So here, this is a current, 1.5 amps of current, and this is a resistance, 10 ohms resistor, and this is the voltage. So for the finding of this VTH, this is the VTH. For the VTH, for the finding of this VTH, if I draw the loop over here, you need to be considered two voltage drops. One is 20 volts, one is 20 ohms voltage drop, another one is 10 ohms voltage drop. For the consideration of 20 ohms voltage drop, you should know the voltage across the 20 volts, 20 ohms resistor. For the finding of 20 ohms resistor, you should depend upon VDR. What is the VDR rule? Total voltage multiply with the 20 ohms by total value of resistance 20 plus 25. Then you will get voltage drop across your 20 volts, 20 ohm resistor. Then another one is 10 ohm resistor. How you are going to be find the voltage drops across the 10 ohm resistor? Here I given the current path. But from this current path, this 1.5 amps of current is flowing in this direction, right? Since this is open circuit, from this 1.5 amps of current is flowing through which path? Since this is open circuit, this obviously choose this 10 ohms resistor. So what I want to conclude is the 1.5 amps of 1.5 amps of current obviously flowing through this 10 ohms resistor. Since this is open circuit path, the current will not going to be flowing through the A and B. So the total 1.5 amps are of current obviously flow through the 10 ohms resistor. Hence, for the finding of voltage drop across this 10 ohms resistor, you should multiply with current and resistance. Already I know the current 1.5 and the resistance is 10. Then you will get total value of voltage across this A and B, means open circuit voltage across this A and B. Also Thevenin's voltage across this A and B. Also VAB is equals to 31 volts. Hope it clear. Please try to observe this way of representing of this VTH. This is very important. Don't confuse about this point. How I added this 1.5. Please observe this point. After this node, observe here. Here the current will not flow. Since the current always choose the short circuit path or closed path. Since this is a closed path of this current, then it will obviously choose this path. So the total 1.5 amps of current will flow through the 10 ohms resistor obviously. Then the 10 ohms resistor which is flowing with drawing with the 1.5 amps, then the voltage drop built across this 10 ohms 10 ohms resistor, that voltage drop is nothing but a 15 volts. 15 volts plus 16 volts. Then the answer will be 31 volts. So this is VTH. This is the way of finding VTH. Now RTH. For the finding of RTH, all the voltage sources are made with the short circuit and current sources are made with the open circuit. So here this is a voltage source. Short circuited, right? Observe here, short circuited, right? Here, this is short circuiting, and this is the current source. Current source is the open circuit. Here, this is the current source is open circuited. I make the open circuit. Now remove this all these extra nodes, extra lines. Then it is clearly visible to you all. This is the circuit. 5 ohms and 20 ohms are parallel. Then the result, which is series with the 10 ohms, that is the total value of across A and B terminals is 14 ohms. 14 ohms across A and B terminals. So now draw the equivalent circuit. So this is the equivalent circuit. VTS 31 volts and RTH is 14 volts, 14 ohms. This is example number 3. So for the finding of total VAB voltage across this VAB, so you should depend upon the you should use the VDR principle. For the VDR principle, for the measurement of VAB, VAB is equals to total voltage 31 into multiply with the same value of resistance. 31 multiply with the same value of resistance 17. 31 multiply with this 17 divided by 17 plus 41 means 31. Then the 17 volts will be present across this VAB. That what I wrote here. So this is way of solving this Thevenins theorem problems. So hope you clear. So let me see one more problem. So in this problem, so determine the Thevenin's equivalent source. Let me add my marker. Determine Thevenin's equivalent is seen from the terminals A and B. This is the circuit. Please focus over here. Don't focus anywhere in this slide. I will explain the steps one by one. So this is the example number. I can name it as example number 4. Here, across A and B terminals, you should measure the VTH and RTH. So for that, you should remove first RL. I removed the RL. Please let me remove this markers. So I removed the RL. See, I removed the RL. After the removing RL, this is my circuit. Right, 100 ohms, 100 ohms, 75 ohms, 47 ohms, 27 ohms. From here, I am going to be measure VTH. For the measurement of VTH, So this is not useful here, 27 ohms. Why? Because I already said the reason. I'm going to be making this short circuiting this. So I'm directly measuring this in the previous session. Sorry, in the not previous session, in the previous slide. Here there is no voltage, there is no resistance, right? But in this slide, I added the resistance to make a little bit clarity about the VDR and CDR rules. So hope. So for the measurement of VTH across this A and B terminals, I removed the load. So after the removing loads, I can measure VTH by using VDR rule, voltage division rule, across the 75 ohms. Total voltage 25, right? 25 multiply with this 75 by total voltage. This is 25, 25, 25 by 75 into total value of resistance 100 plus 70 plus 47. So then the total value of voltage across the 75 ohms is 8.45. This is way of finding the VTS. So now let me move to the RTH. So here this is RTH equivalent circuit. Simply I removed the voltage source by making the short circuiting over here. Please observe here. Then I am going to be measure the resistance across this A and B terminals directly. For the measurement of resistance across this A and B, this 147 are series or in parallel. Obviously, this both resistance are in series because the common value of resistance is connected over here. This 147 means 147, which is parallel with the 75 here. It's parallel with the 75, and the result will be series with this 27 ohms. You can observe over here this representing. You can observe here. Please be careful with the series and parallel circuits. If you do any mistakes, if this is are in parallel, if you do 147 or if you assume that is in parallel, that is a big mistake. If you have any doubts in series and parallel, please go through the series and parallel sessions on your BW at your first semester. Please try to get a knowledge from over there, then come back to these sessions. Otherwise it will very complicated for you guys for the understanding of the circuits. If you very doubts on the series parallel circuits, please try to clear those doubts with your lecturers. Now we are in advance compared to series parallel. Already we know about the series parallel in your previous semester. Now we are moving to the star and delta. If you have any doubt in star and delta, we will discuss it. But series and parallel, you should very clear before this semester itself only, right? So this is the series connection, series 100 plus 47, and which is parallel with the 75 ohms, and which is series with this 27 ohms. Then the result value will be RTH across this A and B terminals 76.7 ohms. So now you got the VTH and you got the RTH. Then the result value will be like this. This is the Thevenins equivalent circuit. This is a final circuit, means equivalent circuit. Thevenin's equivalent circuit. So in this Thevenin's equivalent circuit, you should write RTH, VTH values clearly. But since the RL value is not given, you should directly write the RL across the A and B terminals. So this is way of finding the solution by using Thevenin's equivalent. Sorry, by using Thevenin's theorem. Hope you clear in the slide itself also. You can observe the answers on your below of this slide, 8.45 and 76.7 ohms. Try to practice more problems by using Thevenins theorem, and also practice more problems by using superposition theorem. And we will discuss few more problems in our next session. Don't worry. Please, if you have any doubts, get back to me. Hope you clear this session. Thank you. Thanks for your time. Have a good day. Bye bye.